All right. Today I really want to go through this. This is homework number 1. So in your project number 1, we made a very big assumption. Anywhere we see split, it's an even split. Today we're going to prove that it's wrong. All right? So it's due next Friday. In project number 1, assumption was made for the piping system in an apartment building. In every T junction, the flow rate will split evenly. In this homework assignment, we're going to use Fluent to determine the flow rate distribution to see if it's 50-50 under various flow conditions. We'll use 2-inch pipe. It's very much like our first tutorial, the big elbow. So here, 2-inch pipe. We're going to use 2-inch diameter pipe for this homework. For configuration number 1, we'll do two configurations. Configuration number 1. This is the T junction, this is the main flow, and this is the branch flow. Right? Starting from the origin, this is the origin, the line portion extends 4 inches upstream, and 8 inches downstream. 8 inches down, so the total length is 12 inches. Extend 8 inches downstream, while the branch portion extends 4 inches. The line and the branch perpendicular to each other. Then this is the first case. We'll put a flow rate here. Let's see how much goes through this line portion, how much will go the branch portion. Our intuition tells us the majority should go this way, and a very small portion should go through the branch. Then configuration number 2. All right. So compared to configuration number 1. All we did is add an elbow to the line portion. In other words, what we're doing here is to increase the resistance from the line portion. The branch portion, no difference. The line portion, turn the flow 90 degrees, which means let's add more resistance to the flow. All right? So we can imagine, even before we solve the problem, compared to configuration number 1, the line portion should be reduced. The branch portion should be increased. By how much, we'll see. Right? And for each of these 2 configurations, let's do 2 flow rates. Right? Assignment for water, let's use water, 1.0 kg per second. That's mass per unit time. That's mass flow rate. 1 kg and 0.1 kg. So there's significant difference. Let's see. Let's determine the flow rate distribution at the 2 axes. We call this axis 1, the line portion, and we call this axis 2, the branch portion. Let's see the distribution, the ratio, and show the geometry of the 2 configurations and the contour plots under each flow condition. So, what I would like to see from your homework number 1 is, I want to see figures showing mesh. Once you have the mesh, I want to see that. Convergence, you really have a converged solution. Then velocity contour, after look at the velocity contour and the screenshot showing the flow rate distribution. 95% will go through the line portion, 5% will go through the branch portion. I would like to see your screenshot, not your handwritten numbers, so I know it is a result generated by this computer or by this software. Right? Okay, so let's do the step by step. I want to show you how to set up this flow. All right, so let's see. This is X, Y, Z. What we're going to do is we'll start from the YZ plane. Let's create a new plane. 4 inches in the negative X direction. Then let's create the semicircle and close that, extrude that for 12 inches. Then on the XZ plane, let's create another semicircle, close that, and extrude that for 4 inches. That's how we get this branch portion, line portion and branch portion. That's configuration number 1. Configuration number 2, a little more complicated. Same thing. Let's create that YZ plane. YZ plane. Let's create a new plane, and just like the tutorial, let's create this profile. This is called a profile, and this is the path. This is the path. So let's create a straight line, which is 12 inches long. Then here we'll arc by center. The center is 2 inches above, and the radius is 2 inches. So turn 90 degrees. Then extend 2 more inches. All right. So this exit 1 and exit 2, they're at the same height. This is 4 inches. After we turn this is 2 inches. So turn this is 2 inches, another 2 inch. All right. This is how we're going to create the two geometries. All right. Start ANSYS Workbench 19.1. Then come here, fluid flow, double click. Let's call this T junction 1. Junction 1. Then left click on geometry, left click. Choose the second option, new design modular geometry. And make sure you right click, wait for 2 seconds, and choose the second option. New design modular geometry. New design modular geometry. Working. All right. Units, inch. YZ plane. Click on that. That's YZ plane. Then go up here. We'll create a new plane. New plane. That's plane 4. And come here, let's change the transform 1 of global offset global x. Offset global x, -4. All right. So we create a new plane. Back in x direction, 4 inches. 4 inches. Generate, and on plane 4, click on plane 4, we're going to have a new sketch. Click on new sketch, enter plane 4. New sketch, plane 4. Then we do just like what we did for the tutorial. Sketching, settings, grid, check, major grade spacing, 1 inch, minor steps per major, let's use 2. All right, so we'll have a very nice grid here. And go to draw. We're going to do this circle, arc by center. Arc by center. All right. Just keep in mind our geometry. So here, what we do is first click on the center, which is here, and we have a 2-inch diameter. 2-inch diameter. So the radius is 1 inch. All right. Come down here, one grid, click, and it always goes counterclockwise. Click. All right. So we'll have a semicircle again. Let's take advantage of the symmetry of the geometry. So let's only do half of that. So we'll have this 2-inch pipe, but only half of that. Well, once we create this arc, close it, click on line. All right. Now it's closed. It's closed. All right. So the next step, we're going to extrude. Come to the top here. There is one button here. It says extrude. Click on that. All right. So here under the details, it says 12 inches. That's exactly what we want. We want extrude this geometry for 12 inches. So generate. All right. So this is our line portion of the T-junction. Okay, the next, let's create the branch portion. On the branch portion, it is on the ZX plane. But this time, we don't need a new plane. Let's just go to New Sketch. So first click on ZX plane. New Sketch. Come to the top here, it says New Sketch. So Sketch 2. All right. Go to sketching, settings, grid, check, major 1, minor 2. All right. Let's go to draw. Well, let's do it this way. Arc by center. Right. Center is the origin, and go down 1, click. Right. So, if we click on the y-axis, we're looking down from the y. And this is the semicircle. Now let's close that. So go back to line, click, and close this diameter. All right. This is our sketch 2. Now let's extrude that 4 inches. So come here, extrude. All right. And geometry, extrude what geometry, just click on apply. And this software is smart enough to recognize we're going to do sketch 2. We're going to extrude sketch 2. All right, not 12 inches this time, let's only do 4. Generate. All right, so relatively straightforward. This is our geometry for junction number 1. So we create YZ plane, extrude that for 12 inches. On the ZX plane, we do the same thing, but we only extrude that for 4 inches. Now this is our T-junction. So that's the geometry we want. So now let's go to File, Save Project. Let's save on the desktop. Let me call it Junction 1. junction 1. That's the geometry. That's the geometry. By the way, so here actually we can, before we say that, we can expand this part. This is called solid. We can change the name, rename that as junction 1. Junction 1. And go down here, it is not solid. Enter fluid and solid. It is not solid, it is fluid. Alright. Then we save the project again. Okay. Mesh. Remember, when we do mesh, the first step is specify boundary condition. We'll have inlet and exit 1, exit 2. The line portion, let's call it exit 1. The branch portion, let's call it exit 2. Exit 2. And there is inlet, and there is symmetry plane. Starting mesh.
Did you double click on that?
Mesh, yes.
How would you double click on the
Okay. All right. So this is our geometry. So what we want to do is first name all the surfaces. So this is called exit 2. So click on that. Right click. Create name selection. Let's call it exit 2. Create name selection, exit 1. Create name selection, symmetry. Then hold down the middle mouse. Inlet. The rest of the surfaces, by default, is solid boundary. Yes, it is solid boundary. So that's this part. All right. Then click on mesh. Click on mesh, and what we're going to do is we're going to select this solid, and we're going to insert the sizing function. Insert sizing function. All right. So go to the top. Here it says the default is select face. Now click on the body. Click on the body. Then come down here. Click. Right click. Insert sizing. Sizing. Before you do that, you must click on the mesh first. You must click on the mesh first. So this software understands, oh, you are going to do something to the mesh. You're going to specify a sizing function. Click on the mesh, then select the body. Click on the body, right click, insert sizing. Insert sizing. All right. And if everything goes right, you will see the color change. All right. And these are details of the body sizing. So click on mesh again. Click on the mesh again. We're going to do exactly the same as what we did for the tutorial. So go expand. You can make it up a little bit. So here, expand sizing. All right. Curvature normal angle. Make it 10. Quality, expand quality, smoothing high. Inflation, program control. Right. 3 things we need to do. Right. Undersizing, change the curvature normal angle to 10. Under quality, smoothing high. Under inflation, program control. So 3 things you need to change. All right. Now, click on this body sizing. This is about mesh. Now, about this body sizing, click on that. All right. Click on the body sizing. Now we're going to change this element size. If we still remember from tutorial, that measuring number is 6e negative 3. 6e negative 3 meter. All right. I think that's all we want to do. And let's go to do the mesh. There are 2 buttons we can do it. One is called generate mesh. The other one is called update. The only difference, it will do the same thing. The only difference is if we use update, then when we go back to here, we don't need to update again. If we use generate mesh, then when we go back here, you need to update the mesh. This time, let's try update. Okay. This is the mesh we're going to use. Okay. Click on mesh, you will see the mesh. Again, you can clearly see this is the inflation we're going to use. This is the mesh we're going to use. All right. File, save project. Okay. Pretty much exactly the same as the tutorial. Right. Minimize meshing. See here, if we do update, we'll see this nice check sign. Right? If we use generate mesh, there is something like this. We have to update it again. Right click, update again. It doesn't matter. But here, save one step. Set up. Everything take default. Just like tutorial, let's go down all the steps. Our geometry is important. All right, so here, pressure based, keep that, absolute, steady state, units, lengths, inch. Right. Unit, lengths, inch, close. Fluid will understand we have a 2-inch pipe instead of 2-meter pipe. It's 2-inch pipe. All right. That's all we want to do for general, and let's go to models. This time, we only do fluid flow. There's no heat transfer, so let's do not turn on the energy equation. Let's leave it off. Viscous flow, K epsilon, let's do the same. Enhanced water treatment. All right. So for viscous flow, instead of laminar, we're going to do turbulent, K epsilon model, enhanced water treatment, everything else default. Okay. All right, that's it for models. Materials. Double click on the fluid. We'll see the fluid database. We only have air. No, we want to do water. So here, go to the fluid database. All the way down. Water, liquid, H2O. Copy. Close. See here, we didn't turn on the energy equation, so we only have two properties that matter. Density, 998.2, viscosity, and 0.001, 003. Let's take the default. No, let's take the default. So this is on water. Close. All right, that's all for materials. Next, cell zone conditions. Junction 1. It's a fluid domain. It's a fluid domain. Yes. Edit. Very important. Material name is water liquid. It's water liquid. The default is air. No, we have water here. Okay. Boundary conditions. All right, let's go through them one by one. Exit 1. It is, by the way, when we click on exit 1, it says it's wall. No. It is pressure outlet. It's pressure outlet. It's pressure outlet. Change the type to pressure outlet. Exit 1 is pressure outlet. And here, the way we put the pressure as 0, which means after this T-junction, water exit 1, it will go to ambient. Ambient. Here at top, same thing, go to ambient. We put there as pressure as 0. We do the same. When we specify turbulence, let's use intensity and hydraulic diameter. Intensity, let's give it 5%, and hydraulic diameter, this is 2-inch pipe, so let's make it 2. Okay. Exit 2, exactly the same. Change the type to pressure outlet. Pressure outlet. 0 pressure. Intensity and hydraulic diameter, 5%, and still 2-inch. Inlet, the default is velocity inlet, but here in this problem statement, we're given the mass flow rate. So let's change that velocity inlet type to mass flow. Mass flow inlet. All right. Change the type to mass flow inlet. Mass flow inlet. We know the flow rate. The flow rate is, the first case is 1.0 kg per second. Yeah. And the way we specify the direction, let's make it normal to boundary. Normal to boundary. So here from inlet 1, it is normal to the boundary. It is coming in. It's coming in from inlet. So mass flow rate is 1 kg per second. Turbulence, let's make it intensity and hydraulic diameter 5%. And 2-inch. Okay. Interior is interior, nothing needs to be symmetry. Symmetry, it's symmetry, so it's nothing. Wall, by default, by the way, the type is a wall, so nothing needs to be changed. It's a no-slip boundary condition. All right, that's all for the boundary conditions. Boundary conditions, let's see, controls, equations. Here, we're going to solve flow and turbulence equation. Okay, nothing needs to be changed. I just want to show you. And these are called under relaxation factors. Under relaxation factor. When Fluent is solving all those equations, we use under relaxation factor to control how fast we want to move. We want to advance our solution. How fast we want to push forward to get to the final solution. And these are the default numbers. We'll take that. Of course, the higher the number, the faster we can approach the final solution. But the thing is, if it's too fast, there is danger. The solution will blow up. It's just like when we're driving. Too fast is not a good thing. Many times. All right. Anyway, initialize. Run the calculation. Let's give it 300. This is what we want. All the residuals are going down. What I'd like to see from your homework one is I want to see all these lines they level off. Which means see this is still running. 300 is not enough, so let's make it 300 more maybe. All right, it says calculation complete. All right, this is another thing. You see that they're still going down. All the residuals are still going down. So go to monitors. Residuals. And here, these are the default target for this convergence. See, this is 3 order of magnitude reduction. That's the default. And many times it's not enough. You see, all these lines are going down, still going down. So what I would like to do is, for this continuity equation, let's put 2 more zeros. Instead of 0.001, let's give it 2 more. Right? And usually, this continuity equation, which solves for the pressure, it is always the hardest one to convert. So you don't need to change everything, just the first one. Right? So I want this to continue. Okay. Then go to run calculations. And it shows the residual value. This is what we want to see. So all the lines, they become horizontal. So here the residuals, the stabilize. So here we have reached a final solution, which means continuation of this running will not give us any more accurate solution. We have a converted solution already. It's finished. All right. So when you turn in your homework, I would like to see at least a portion of your calculation. I would like to see all the lines. They become horizontal. All right. Okay. So I would like to see the distribution. First, let's see the plots. So graphics. Contours, fill. I want to see velocity on the symmetry plane. on the symmetry plane. Yeah. In your report, in your homework, I would like to see this figure. I would like to see this figure. So after you'll get a converged solution, and this is what I would like to see. So here, this is the velocity magnitude, and you can see red means high velocity. This means low velocity. You can see clearly majority of the flow is in the line portion. Only a very, very small portion goes to the junction. But I would like to see the distribution. So here, if you go to and the results, go to reports. Go to reports, surface integrals. So surface integrals. All right. Mass flow rate. I would like to see reports, surface integrals. So the integral means some mass flow rate from what surface? From exit 1 and exit 2. I would like to see the mass flow rate distribution. Don't forget, when it comes in, it's 1.0 kg per second. Compute. So after you select exit 1, exit 2, compute. All right. Now this is a screenshot I'm talking about. When you turn in your homework, I would like to see this. And so here, mass flow rate from exit 1 in terms of kg per second, about 95, and exit 2 only 5. So here, negative sign means it is leaving the domain. Into the domain positive, leaving the domain negative. So both exit. So this is what I would like to see. So our assumption is wrong. It is not 50-50 split. Actually, for this particular case, 95 to 5. Well, you may say, well, how about, we still have 2 minutes, so let's quickly run this. Let's change the boundary condition. Go to boundary conditions. Inlet 1. Instead of 1, let's make it 0.1. Okay. Now we'll go to initialize. Initialize. Get rid of. Do you want to discard the data? Yes. Then run the calculation. Go. 600. This time, so let's remember, for 1 kg per second, it's 95 to 5. Here, let's reduce that to 0.1 kg per second. Just from our intuition, 95 will go up or down. Down. Super. It's going slowly, so the water will have more time to go to the branch. All right. It's just from our intuition. Let's see if we can see that distribution. All right, 600. So seems all the lines just turn horizontal. So here maybe when you turn in this, I would like you to run 200 more. But here, yeah, let's run 200 more. So let's give it 800. All right, I think that's enough. So here, let's go down to see the reports. So go to reports, surface integrals. Let's look at the mass flow rate, exit 1, exit 2. So we expect 95 will go down, 5 will go up. Let's see. 90, 10. 90, 10. All right.